We're continuing with Chapter 3 in the trigonometry textbook. In this video, we're going to go through Section 3.2, which is on applications of radian measure. Now, in the previous videos, as we talked about what are radians and the definition of radians, I've already mentioned what probably is the main application and how it's defined to where it's more intimately related to existing mathematics. And also I've mentioned how it simplifies the definition of trig functions, which we're going to see in the next video. Also, it allows you to easily model motion or something that's circular. That's the idea of how the trig functions become like what are called circular functions when you use radians. Also, when you take calculus and learn derivatives of trig functions, radians make the derivatives of trig functions very simple. So the derivative of sine x, for example, is just cosine x. That's it. But if you used degrees, it would be this derivative. If x was in degrees, it would be you get this extra factor here. So you see with radians, it makes a lot of math, physics, etc. a lot cleaner. So there's different applications or aspects of using radian measure that make things more useful. And in this section, we're going to talk about a few of these applications. Okay, arc length on a circle. The formula for finding the length of an arc of a circle follows directly from the definition of an angle theta in radians, where theta is equal to S over R. So yeah, this is like the definition of radians, right? You have an arc length of a circle, S, a certain arc length, and you can associate with that arc length an angle that has vertex at the center of the circle, and that angle like sweeps out that arc length. With any arc length of a circle, you can associate with that an angle. But like by the definition of an angle doesn't need a circle to be defined. But you can still think about any angle you could associate with the arc length of a circle by putting the center of the circle at the vertex of the angle. Okay, now that circle is going to have a certain radius. So if you divide that arc length by the radius of the circle, then you get that angle. That's the definition of radians. Okay, so what they're saying here is that if you want to find the arc length of a circle, then just come to the definition of radians. The arc length of a circle is r theta, where theta is in radians. So in figure 5, we see that angle QOP has measure 1 radian and intercepts an arc of length r on the circle. We also see that angle ROT has measured theta radians and intercepts an arc length of S on the circle. Yeah, so here, 1 radian, that means that this 1 radian angle intercepts an arc length of length R. Here, theta radians intercepts an arc length of S, where S is R times theta. And so there you go. There's the length of an arc. If you're using radians, that's very simple, right? Okay, so the length S of the arc intercepted on a circle of radius R by a central angle of measure theta radians is given by the product of the radius and the radian measure of the angle. Okay, so there you go. There's the arc length formula, where theta is in radians. So yeah, if you come here, it cautions that theta must be in radians here. And I've mentioned this before, but you have to be careful. Like if you see cosine of theta or a trig function, you could interconvert between units, between angle units, and like radians or degrees or really any other angle, because angle is just angle. They all mean the same thing. It's like the amount of separation between two straight lines, the amount of rotational separation. So the trig functions apply to any angle. You could evaluate a trig function, I mean, as long as your calculator is programmed to do it. But even if you did it manually, like if you knew how to do the numerical method that the calculators do, you could do that for any trig function. You could do that as long as you knew what that angle was. Like you could convert that angle to something you're familiar with. So like there's different angle measurement systems other than just radians and degrees. If you could convert that to like something, I think, what is another one? Gradians maybe, any angle that anyone gives you, if you can just convert it to degrees or radians, now you know where that angle is in the plane. And you could do the trig functions, right? So The trig functions, what I'm saying is the trig functions, the angular input is any angle. But a formula like this, whenever you see formulas that where the theta is outside of the trig function, like this, S is r theta, you can't just say, I'm going to convert to degrees and input degrees in here. It doesn't work that way. You need a whole separate formula for arc length if the angle is in degrees. This is just for radians. Okay, so it says here, a circle has radius 18.2 centimeters. Find the length of the arc intersected by a central angle having each of the following measures. So, yeah, the arc length, so 3 pi over 8 radians. And, I also want to stress here that this arc length doesn't have to, it's not like this has to be measured from the 3 pi over radians, like from standard position. Like, 3 pi over 8 would be, that's less than 1/2. 3 over 8 is less than 1/2, so it'd be in the first quadrant. It doesn't have to be, this. 3 pi over 8, what's this arc length? It could be anywhere. Three pi over 8. What's the what's the length of this arc? That's what they're saying. Like, this arc is intercepted by this angle. So what's the arc length? Okay, well, the radius of the circle is 18.2, so just multiply that by 3 pi over 8, and you're done. Here, you just need to convert this to radians, then multiply by 18.2. And why does that work? Because okay, so 144 is somewhere out here, but I like showing this not from standard position. I think it's a better illustration. Okay, so if this is 144 degrees, right? So if you convert this to radians, when you do a unit conversion, you're not changing the actual physical nature of what you're talking about when you just change units, right? Angle is angle. Angle means the exact same thing in radians as it does in degrees. So when you convert 144 to radians, you're just erasing this and putting that in radians. It's the exact same arc. So if you convert this to radians, that's what they do. They get 4 pi over 5 radians, multiply that by 18.2. That's the length of this arc that's intersected by 144 degrees. See? Okay, finding the distance between two cities. Latitude gives the measure of a central angle with vertex at the Earth's center, whose initial side goes through the equator and whose terminal side goes through the given location. Reno, Nevada is approximately due north of Los Angeles. The latitude of Reno is 40 degrees north, and that of Los Angeles is 34 degrees north. Yeah, the north means north of the equator. The radius of Earth is 6,400 kilometers. Find the north-south distance between the two cities. Okay, yeah, so latitudes and longitudes, the reason why they're called angles is, so if we take a look here, so latitudes are the horizontal the horizontal lines around the globe. They're horizontal circles, and the radius of the latitude gets smaller and smaller as you go more north of the latitude circle. Longitudes, I think longitude, the word long, they're longer. They're vertical. They're the vertical lines. They're these vertical circles. And the angles, what they're talking about is, so like you have these latitude lines, right? And to specify a latitude line, you say like 30 degrees, and you'll say north or south. And the north or south is referring to above or below the equator. So if you were specifying this latitude here, this third latitude line, you would say 30 degrees north, and that's that latitude line. Now you get really specific if you can pinpoint like someone's house, or like the one of the great pyramids, for example. You could pinpoint that location. And how do you do that? Because they divide this up into minutes and seconds. You'll see coordinates in fractions of a second. Like the coordinates of the Great Pyramid is like something 54 minutes 37.3 seconds, right? It's like the exact coordinates. down to like seconds or maybe even fractions of a second. But that's how you specify a latitude line. And then a longitude line will be, so latitudes go from 0 to 90. It's either 0 to 90 degrees north or south. Longitude lines you can see are going to go from 0 to 180, and then you'll specify east or west. And that line is the prime meridian. Is like the equator is the 0 line, and then the prime meridian is the 0 for longitudinal. Okay, so they're saying that the latitude of Reno is 40 degrees north, and that of Los Angeles is 34 degrees north of the equator. We're talking about, they're specifying latitude lines. The radius of the Earth is 6,400 kilometers. Find the north-south distance between the two cities. So yeah, you can see the circle is the prime meridian. You think about the circumference of the Earth, but if we come back from the perspective of the prime meridian, that's what, when they say the radius of the Earth, that's what they're talking about. From like the center of the Earth, the center cut, the prime meridian. Well, I guess you assume that the equator and the Earth is a sphere, so that both the equator circle and the prime meridian circle have the same radius. But, okay, so that's the circle. And so we're tracing out an arc of the circle from Reno to Los Angeles. And Los Angeles, it's the latitude is 34 degrees and Reno is 40 degrees. So this is 6 degrees. Okay, so now if we just find the arc length here, that's the north-south distance between the two cities. And you might be saying, well, no, isn't this the north-south distance? Well, no, because you're not driving into the Earth. You don't notice the curvature of the Earth when you're driving, right? And we're just looking at the distance between the two latitude lines from Los Angeles and Reno, right? It's strictly north to south. So, okay, 6 degrees times the radius of the Earth, and we got it. No, that's wrong. We have to convert this to radians first to use that S is equal to R theta formula. So 6 degrees, they convert it, it's pi over 30 radians. Multiply that times the radius of the Earth, and there you go. 670 kilometers. Okay, here it says a rope is being wound around a drum with radius 0.8725 feet. So a rope is being wound around a drum, or like you could think like a chain being pulled in by a winch or something. How much rope will be wound around the drum if the drum is rotated through an angle of 39.72 degrees? Okay, so yeah, you can think about coming across an application like this. If you know the drum rotates through 39.72 degrees, how much rope has been pulled in? Well, how could you figure that out? Well, what you're thinking about is, if you start here, right? Let's say this is where you're starting. You haven't pulled any rope in yet. And now the drum rotates 39.72 degrees. How much rope is pulled in is whatever the length of that arc is. That 39.72 degrees, the arc that's created by the drum. That's going to depend on the degree, the angle, but also on the radius of the drum. So you have to convert this to radians and then multiply that times the radius of the drum. And that's how much rope is wound in. All right, 2 gears are adjusted so that the smaller gear drives the larger one, as shown in figure 9. If the smaller gear rotates through an angle of 225 degrees, through how many degrees will the larger gear rotate? Okay, yeah, this is interesting. So we've got the radius of these 2 gears. If this small gear rotates 225 degrees, then how much does the larger gear rotate? How can we figure that out? So you analyze these kind of problems a lot in engineering. And the key idea here is that what do these 2 gears have in common since they're mated? Well, at their contact points, at the point of contact, at the mating point, they have the same velocity, like the gear teeth. So like the circumference. Think about the circumference of the gear, the mating kind of circumference. They're moving at the same speed. They have to be. I don't want to say the gears are moving at the same speed because we're really talking about the circumference circles are moving at the same speed. And so with that, what you can think about is, so take like a any time interval, like 1 second, let's say. I don't know how long it took to do this rotation, but the amount that the circumference of this gear rotates in 1 second is going to be the exact same amount that this rotates, at least their circumference. That has to be the case if they're mated like that. So what that means is that the total distance, like the total amount of arc, like if you measured, like if you had a rope here like this, right? And you could kind of string out rope coming from this gear based on how much it's rotating, and you could also string out rope from here based on how much it's rotating. It's going to have to be the same amount of rope. Now, the smaller gear, it would have to move faster, right? Because we know that the amount of rope is dependent on not just it would be dependent on the speed, but it's also the radius, right? This would have to spin faster, but it's going to be this. It has to be the same amount of rope coming out because they're mated. And so with that, what we can do is we can get the total amount of arc length that 225 degrees corresponds to on this gear, and that must be the same amount of arc length that this gear rotated. And then with that we can figure out what angle that corresponds to. It's going to be a different angle here because it's a different size circle. So that's what they do. They convert 225 to radians here, and then they multiply that times this radius and get this arc length. Then they rearrange the formula as S divided by R, and they divide this by this radius. And they get this in radians, and they convert that back to degrees, 117 degrees. Okay, another application of radians, it has to do with finding areas of a sector of a circle. You can imagine radians simplify any kind of geometry calculations related to circles for sure. But what you can see is that, it's not just, this isn't just about geometry. Circles come up in machinery and all kinds of real life applications, not just literal geometry. Circles are everywhere. All right, the sector of a circle is the portion of the interior of a circle intersected by a central angle. So like this is a sector. It's an area. A sector is an area. Think of it as a piece of pie. Okay, a complete circle can be thought of as an angle with measured 2 pi radians. If a central angle for a sector has measured theta radians, then the sector makes up the fraction theta divided by 2 pi of a complete circle. Yeah. I mean, but you could just as easily do this with degrees, right? Theta divided by 360. If you have an angle of 30 degrees, what's the area of the sector? Well, you just do 30 divided by 360, that's a fraction, and multiply that times the area of the circle, pi r squared. That's what they're saying here. In radians, theta divided by 2 pi, multiply that by the area of the circle to get the area of the sector. So far, radians hasn't done anything special relative to degrees. Okay, the area of a complete circle with radius r is pi r squared. Therefore, we have the following. Yeah, so theta divided by 2 pi times pi r squared, there's the area of the sector. And so what happens is with radians, these pi's cancel. And you just have 1/2 r squared theta. That wouldn't happen with degrees, right? You have theta divided by 360 times pi r squared. Okay, so there's the area of a sector where theta is in radians. But it cautions, it says that theta has to be in radians. You can't convert to degrees and plug it in like you can do with trig functions. Okay, so here they give an example. So a center pivot irrigation system provides water to a sector-shaped field with measures shown in figure 11. So yeah, irrigation kind of works this way, right? You have those irrigation systems with the nozzle. It's spraying and it's kind of just pivoting left to right. And it's kind of spraying out a sector. So what's the area? They're saying the area of the field, but I would think about it more as the coverage area of the sprinkler. And so it's spanning 15 degrees, and it has a radius of spray that so just convert that to radians and do 1/2 the radius squared theta in radians. Okay, but we're going to work a bunch of examples so you can get the feel for this and get a sense of different potential applications.